This is lesson 49 of the Quantum Mechanics, a mini lecture series titled Vectors, Part 1. So when you want to know how fast you're going along a road, let's say, you simply tilt your head down and look at the speedometer. Okay, that's your speed. Okay, now if you decide to add a direction to that speed, let's say 50 k's per hour, south, then this is what we call a vector. Okay, so speed 50 k's per hour. Okay, we call this a scalar. Okay, a scalar is a number. Okay, temperature is a scalar. Speed is a scalar. Speed with a direction, that's a vector. This is called velocity. Okay, velocity is the same thing as speed, but with direction. So velocity is a vector. Force is also a vector. Let's say weight force, okay, which acts downwards. We often use the symbol V, okay, lowercase v for vector in physics with an arrow on top of it, like that. Now, I sometimes write it like this, half an arrow. Okay, these are equivalent ways of writing vector V. We can even write it, I sometimes see it like this, with a tilde at the bottom of the V. These are all equivalent notations for vector, vector V. Now, in maths and even in physics, there are vectors which have components, right? Okay, components are basically parts to it, okay, pointing in different directions. Here's how we typically write this in mathematical form. V arrow is equal to x, y. And I should also mention sometimes the V is just a bold V, boldface V as well. That's another way of writing V vector. So x, y, this means that there's two components to the vector V. In other words, this vector here is two-dimensional, okay, because it's got two coordinates, x and y. And we can plot these two coordinates on a number plane. So y at the top, x at the bottom. Let's suppose we'll pick some arbitrary point here, x, y. Okay, that's the vector V. It's an arrow, it's got a direction. Let's call that vector V. Okay, it's got some y component and some x component. A vector in two dimensions, okay, in other words, it's along the x and y axis, say, can also be represented as follows, okay? A V1 plus B V2. Okay, A and B, these are just real numbers. These are the coefficients of the components V1 and V2. These are the components. These are the parts of the vector V. Okay, V1 and V2 could stand for X, let's say, and Y respectively. And theoretically speaking, you can have an infinite number of terms, okay, in this linear combination. This is called a linear combination. So this thing up here, this thing here is called a linear combination. Linear in the sense that there's no square terms. It's a combination of linear terms. It's called a linear combination because it's combining components. And what the components V1 and V2 tell you, they tell you how much of V1 and V2 you need to make the resulting vector V, right? There's a property of vectors called, I should mention as well, linear independence, interdependence, linear independence. So in this case, in the case of two dimensions of space, the vectors V1 and V2, these are said to be linearly independent if they satisfy the following condition. Okay, if you plug in any two vectors V1 and V2 into this relation, multiply them by constants A and B, you get 0. They're called linearly independent. Okay, in other words, A is equal to B is equal to 0, okay, for some combination. And these two vectors V1 and V2, these express the vector V in its component form, right? So the components V1 and V2. And these are the basic tools needed to write any vector. And hence we call these two vectors basis vectors, okay? They form the basis for describing a vector V. And when it comes to determining the number of dimensions of our space, we can use the number of basis vectors to tell us how many dimensions we're dealing with. In this case, dimensions, there's two dimensions here, two-dimensional space. If we have V1, V2, V3, okay, three vectors, that's three-dimensional space, and so on and so forth. In the next video, I'll talk more about some properties of vectors.